So hello everyone. I'm Yousra from Syracuse University, and today I'm presenting my paper, Harvesting Inconsistent Security Configuration in Custom Android ROMs. So as we know, the open nature of Android ecosystem has laid the foundation for a highly fragmented operating system. The OSP have been aggressively customized by everyone in the customization chain. Vendors and hardware manufacturers' carriers are free to build upon the baseline to customize the devices for different models and regions. For example, vendors might add new system apps, modify existing ones, and also they might even change the framework itself to include more sophisticated features and services. A prominent example is Samsung's Knox, which is a multi-layer security platform that allows sophisticated security features to users. What's further complicating the process is the fast pace with which the OSP updates its OS versions. In fact, since 2008, there is 23 different OSP different versions. So here are some of the facts about Android fragmentation. This figure is from open source, OpenSignal, and it shows how the market is divided in terms of device vendors. So here there is, in August 2015, there was more than 1,200 distinct device models where the majority belongs to Samsung. Each vendor is further divided into different models. The second figure shows that the operating system itself is highly fragmented. So at each point of time, there might exist more than one single version at a time running. Well, thing to know here is that Android customization is not well guided, it's unregulated and decentralized. So because of that, definitely compatibility and portability issues might arise. But now an app developer has to make sure that his app works seamlessly across all different hardware and API versions, which is not really feasible in real life. And Google advises new security updates each month. And those updates might not be really pushed by device vendor to older devices because they are focusing on newer ones. So update problem is one of the security effects of vendor customization. But the Android literature is full of other examples that show that vendors introduce a lot of problems. At the Linux layer, the work called Perils of Fragmentation shows that device drivers are the protection of device drivers might be changed by vendors, and the protection might be actually weaker than the original ones on corresponding OSP. The work Impact of Vendor Customization assesses the security of vendor preloaded apps and shows that it's actually riddled with security flaws such as permission redelegation, content leaks, and pollution attacks. In the context of inter-app communication model, a vendor might decide to remove an existing app, or he might decide to change the attributes of an app. For example, here, application A is renamed to application B prime. And now application A, which was referring application B, is not anymore referring to an existing attribute. So now the reference to application B and application C is hanging. So our work shows that malicious app can squat this missing attribute to conduct several damages. In this work here, we aim to generalize the findings on existing customization hazards to come up with more problems that might be introduced by vendors. All identified vulnerabilities on Android customization are due to the fact that vendors might alter configuration at a specific layer. But despite the serious consequences, there is no work that systematically tries to find all security configuration changes caused by vendor customization. So our question is, can we systematically identify all security configurations at each layer? So again, if we map the existing work to the Android layered architecture, what we want to do is generalize from this works and then try to see if from those generalization we could find more secure risks that have not been yet discovered. So basically, we make the first attempt to systematically detect configuration changes introduced by parties in the customization chain. And our key intuition is by comparing custom device to similar devices from different vendors, carriers, and regions, we might be able to find unintentionally introduced configuration changes. So the works that have been studied so far addresses if vendors change the access control on system apps, or the Perl's fragmentation addresses if vendors change the access control at drivers. What about other access control applied at other layers? Can we check if they're the same across all custom ROMs? So we propose to leverage a differential analysis among a large corpus of Android ROMs, customized Android ROMs, and this is our methodology that we followed. So in the first phase, we rely on our domain knowledge and Android documentation to come up with a set of features that, if altered unintentionally, might introduce security problems. And then we check in the second phase, we try to generate those features in the second phase from our custom Android ROMs. And in the third phase, we perform differential analysis to find all security configurations that have been changed across versions. So if we find that one single image has different attributes compared to other images, then we flag that. But we believe that those changes might not actually be problematic all the time. So that's why in the last phase, we came up with a set of patterns that we think if an inconsistency follows them, then those inconsistencies are actually dangerous. So during the feature extraction, we want to find all features that are security relevant and customizable by vendors or other parties. So to find those features systematically, we started from the Android layered architecture. So at the framework layer, and the system services can rely on the caller's permission or caller's UID or package name, package signature to check if the caller has the right to invoke specific API. And at the Linux kernel, the Linux relies on the discretionary access control, that is UIDs and GIDs, to check if the caller has the right to access a resource. And application can make sure that its components are safe and protected through several mechanisms. First, it can make the components visible only to itself, or it can require the caller to have specific UID, or the caller to have specific permission check, or it should be system, for example, the case of protected broadcast. So basically, this is a summary of all the features that we have extracted. We don't extract UID and package name and package signature because package name and signature have already been covered in our Hare Hunter paper last year. So basically, we just try to extract the other features. So the first feature that we want to discuss is permissions. So Android already provides some built-in permission to protect resources, but also developers are free to define their own permissions. And permissions are assigned different protection levels based on the resource that they are trying to protect. Signature permission are protecting the most privileged resources. Dangerous are protecting less dangerous resources. And normal permission are protecting the very least privileged resources. So here is how permission is defined. And one we want to answer is, can the same permission hold different protection levels across two images? For example, on the first ROM, read SMS is protected with a dangerous level protection level, while on the second ROM, it's protected with a normal protection level. So this type of inconsistency is quite dangerous because it means that developers will be confused, first of all, because they don't know what is the permission meaning. And second, the resources using this permission will be definitely at risk. The second feature that we want to extract is GIDs. So in Android, certain permissions are mapped to GIDs. That is, once an app is granted that permission, it will be running with that GID attached to its process. For example, here, if an app can get this permission, ISAT permission, it will be running with the system GID attached to the process. And basically, that would allow it to access all drivers that are available to the system GID. Of course, we know that system GID is quite dangerous, so that's why the system will protect with the ISAT permission with protection level signature. So only system apps can be granted that permission and thus get the GID system. My question is, can vendors define problematic GID to permission mappings and thus lead into downgrading the GID privilege? So for example, on the first ROM, we have the same GID system mapped to IZ, and IZ is signature level. While on ROM 2, the vendor introduced another permission, for example, custom permission here, but that permission is mapped to a normal protection level permission. So in that case, a normal user, a third-party app can actually be granted the system GID, even if only when it's requests a normal permission level, protection level permission. So this is definitely quite dangerous, as the GID can be acquired with less privileged permissions. Protected broadcast is another feature that we look at. So an application can make sure that only the system is able to invoke certain broadcast receivers within it. So now only system can invoke it, but third-party application cannot. And this is how protected broadcast can be defined. So here we have a boot completed protected broadcast definition. And to use this protected broadcast, an app can declare this action within the intent filter of certain receiver. Here we have receiver A is listening for that action. And our question is, are protected broadcasts the same across all images? For example, and if a protected broadcast is not defined, is it still used within that image? For example, on the ROM 1, boot completed is defined and it's used by the receiver A. But on ROM 2, the boot completed protected broadcast is not defined at all. However, we see here that receiver A is still defined in this app and it's still listening to that protected broadcast, what it thought it was a protected broadcast. So this is quite dangerous, as now receiver A can be invoked by any third-party application. Another feature that we looked at is component visibility. So components can protect themselves by making themselves only invocable by application with the same signature or through the exported flag. But do components have the same visibility across all images? So for example, in ROM 1, this component is exported, while on ROM 2, it's not exported. So this can help us detect unintentionally exposed components. So similarly, we looked at component protection. So components can also require the caller to have certain permissions, but are these permission protection the same across images? For example, here we have the service A is protected with permission A on the first ROM, but it's protected with permission B on ROM 2. So for the data generation, we aim to conduct large-scale differential analysis to find inconsistencies. And for that purpose, we have collected 591 images customized for different purposes. We have images from 11 distinct vendors and from different versions. We have developed a tool, DroidDiff, that would extract all the security attributes from the images and perform differential analysis. So here is an example of an inconsistency that we want to reveal through our analysis. We have two images, Xiaomi Mi to A running 4.1.1 and Xiaomi Redmi 1 running 4.4.2. As we see from this map, there are three attributes, three features that have different values. If you look at the camera GID, that's the most dangerous one. On the first image, it can be acquired with dangerous permission, but on the second image, it can be acquired with the normal permission. That is, on the second image, a third-party application can access the camera driver with the normal permission, which is quite dangerous. So we want to reveal three levels of information about any detected inconsistency. So who's the responsible party? What is the overall situation? And what are the potential dangerous patterns behind these inconsistencies? Meaningful inconsistency should give us insights about who caused it. For example, is an inconsistency due to updating the OS version or customizing model for a specific region or changing a vendor? So for that purpose, we clustered our images based on common criteria. And we've proposed 5 sample selection algorithms for this purpose. For the first one, cross-version analysis, we want to find if upgrading the OS would introduce inconsistencies. So for that, we need to compare devices within the same model. And then for cross-vendor analysis, we want to check if a change of model introduces some different features. For example, an HTC phone has different features compared to a Samsung phone. And for cross-model analysis, we want to find if models within the same vendors also have different features. For example, is a Samsung Edge 6 different from Samsung S5 or S4, given that they are running the same OS version? For cross-region and cross-carrier analysis, we aim also to find inconsistencies that are due to change in the carrier or change in the region. And of course, we need to compare devices running the same model and the same OS version. Now the following figure shows the overall situation in our collected images. And as we can see here, there is a lot of inconsistencies that have been detected by our tool. The cross-version analysis followed by cross-vendor analysis introduced the higher number of inconsistencies. To understand what it means, let's look at the first bar here. So here we find that more than 50% of the candidate image set contain at least 4.8% of permissions with different protection levels. That is, permission holds a protection level, let's say normal on one image, but it holds another protection level on another image. And the number is around 30 permissions. So we believe that not all inconsistencies are actually dangerous, but if they follow specific patterns, then they are definitely dangerous. So we came up with a set of patterns, and then through investigating the results of our analysis, we want to reveal if inconsistencies follow those patterns. And if they do, then they are probably problematic. So the first pattern is if permission goes from normal to a signature protection level, then it's definitely problematic. So on average, we found that 4.8% of common permissions have a protection mismatch, but we're not sure which combination of permission is the most frequent. So we analyzed our inconsistencies, and we found that they're actually normal to signature combination is the most common. So an example is this permission, SIM card authentication. It holds a signature and normal protection on Samsung S4 and Sony Xperia respectively. So this is quite confusing to developers because he might use this type of permission to protect a dangerous resource, but it actually means normal protection on certain images. So another pattern that we thought of is usage of specified protection level is not well understood. So Android allows developers to define permissions with unspecified protection level. And in that case, the default value assigned is normal. But we find that it's not clear whether developers really intended to use normal as the protection level. So we analyzed which protection level is assigned to other images for those permissions that are defined with an specified protection level on at least one image. And we find that unspecified and signature combination is the most common. That is, developer probably thought that signature permission level will be assigned to those permissions that are defined with unspecified protection. And another pattern that we look in is GIDs privilege might be downgraded. For this, we actually found we discovered 3 downgraded GIDs: system, camera, and media. So system and media GIDs are usually mapped to system or signature level permissions, but we find on some specific images they are mapped to normal permissions, which is quite dangerous. Now they can be obtained with normal protection levels on those victim images. So as a result, critical drivers can be accessed because of that. During our analysis of the inconsistencies, we found a bug due to duplicate components, and we reported it to Google. So we found that most of inconsistent broadcast receivers are caused by non-safe practice that developers follow. Developers declare duplicate broadcast receiver names in the same app, but give them different protection. For example, here, we have two different receivers, but they have the same name. The developer wanted to protect the functionality invoked when sending the action reset fail with reboot permission, but he didn't want to protect the second receiver with any protection when sending the action data router display. So due to a bug in the package manager service, the way it handles this duplicate component receiver in its mapping permissions, we found that it's possible to bypass any permissions that are declared on the first receiver. So in this case, we can actually bypass the reboot permission if we want to invoke this receiver explicitly. So here we summarize all the attacks that we find based on the analysis of certain inconsistencies that we found. So on Samsung Edge 6, we were able to read all user emails without any permission, and that was due to an exposed content provider. And in Samsung S4, we're able to reboot the phone without any permission, this action is actually restricted to system apps, and that was also due to an exposed receiver. And in Node 2, we're able to send SMS messages without any permission. And in a prominent example here is on Moto X and several Nexus devices, we're able to send emergency broadcasts without any permission. Other cases is a case that we did on Samsung Edge 6. So we're able to factory reset the phone without any permission and thus delete all user data without any user confirmation or permission. And in other devices such as Blue and Xiaomi, we're able to access different drivers with normal level permission. And so in summary, we generalize the Hell vulnerability and other reported vulnerabilities to conduct an investigation about inconsistent security configurations. So we conducted a systematic investigation to reveal security features that can lead to vulnerabilities if changed unintentionally. So we leveraged differential analysis to find inconsistent security configuration, and we confirmed through a high-level attack that these consistencies can lead to serious security vulnerabilities. And thank you.
Questions?
I'm Pomjin from Rice University. Did you have any trial to compare with the Nexus device?
I'm sorry?
Did you have any run a DroidDiff for the Nexus device between different?
Yeah, we did.
Okay.
But comparing Nexus devices didn't introduce a lot of inconsistencies. They're quite similar.
Okay.
Yeah.
And one more question. How did you get those 500, I mean, about 600 images?
Oh,
you know?
So most of them are from Samsung, and we got them from Samsung Albeit website. So that's where most of the images are. And other images, we got them from physical devices and also from other websites that provide images. Yeah.
So I have a question. For a given model line, it seems like you could look at things in terms of the versions, subsequent releases of the operating system and point releases, and then you could then assess for particular models or particular carriers, over time, do they become more permissive or less permissive? And then you might use that to think about, well, which carriers or which handset providers actually invest in having security staff that thinks about this. Were you able to get any even ad hoc sense of certain combinations being less likely to trend towards less secure configurations, or is it?
Yeah, so we found that non-popular devices, for example, like Blue or Xiaomi, their security features are not actually being updated. They're getting weaker in newer versions. But at Samsung devices, we found that a lot of updates introduce stronger security features.
Okay, so it's consistent with a model where if you have a bunch of money, you can invest it in security, and if you don't, then things are worse. Did you try to contact any of the manufacturers about this?
Yeah, we contacted HTC and Samsung, and also Google for their Nexus devices, and all of them acknowledge our findings.
Okay, great. Other questions? Okay, thank you very much.
Sure.